Hello everyone. Till now, we have understood the root directory as well as the various indirectories. Today, we are going to uh, study what are the various file permission commands are there in Linux. But before that, first of all, we need to know why file permissions matter in Linux. See, we have multi-user system. Linux is designed for multiple users to share files and resources simultaneously. Whether you are running a personal computer or a server hosting hundreds of users, the system must manage who can access what information. Then security protection. Permissions act as your first line of defense against unauthorized access or any malicious changes. Without proper permission settings, any user or program could potentially read sensitive data or can modify critical files in your system. Then system organization. See, proper permissions keep your system organized and prevent any accidental modification. They ensure that configuration files remain intact, user data stays private, and system executables can not be tampered with. So think of file permissions as the gatekeepers of your digital fort. Every file and directory has a security label that determines who gets to peek inside, who can make changes, and who can run programs. In a world where cyber threats are increasingly sophisticated, understanding these basic scrutiny mechanisms is essential for any Linux user or administrator. So, without proper permission management, your system becomes vulnerable to data breaches, accidental deletions, and any unauthorized modifications. So, the beauty of Linux permissions is that they are both powerful as well as flexible. Once you understand the basics, you can create sophisticated access control schemes that perfectly match your security requirements. All right. Then we have the three basic permission types. So here are the various permissions, types of permissions in Linux. So every file and directory in Linux has three fundamental permission types that control what actions users can perform. So these permissions work together to create a layered security model. First is read represented by R. So the read permission allows users to view the contents of a file or list the contents of a directory. For files, this means you can open and read the text or data. And for directories, it means you can see what files and subdirectories exist inside. For example, you can open a text document and read its contents. And similarly, for example of a directory, you can list files using ls command. All right. Then we have other permission, which is write, represented with W. The write permission gives users the ability to modify file contents or change the contents of a directory. For files, this means editing, overwriting, or truncating the data. File example includes you can edit a document and save changes. And for directories, it means you can create, rename, or delete files within that directory. So the directory example includes you can create new files or delete existing ones. All right. Then the third permission is execute, which is represented with X. So the execute permission allows a file to be run as a program or lets users enter a directory. Program files. This means that the file can be executed and run. Like for example, you can run a shell script or or a program. All right. And then for directories, it's required to access it's required to access. That means it's required to enter the directory and access files within it, even you have read permission. All right. So the directory example includes you can cd into the directory. You can write command cd into the directory and access its contents. All right. So these three permission types form the foundation of Linux security. Every file and directory has these permissions set independently for the three different categories of users: the file owner, the group, and everyone else. So we have three different category of users that we will study in the next slides. So this creates a flexible system where you can grant different levels of access to different users or groups. Now, who gets permission? The categories of users. Linux divides users into three distinct categories when applying permissions. So we need to understand these categories, and understanding these categories is also crucial for setting the right access levels for your files and directories. So we have the first type of user, which is owner. The user category refers to the file creator or designated owner. When you create a file, you automatically become its owner. All right. And have special privileges to change its permission. So the owner typically has the most extensive access rights. The key characteristics of this kind of user is sets automatically when the file is created, can change permissions on their own files, usually has full read, write, and execute access, and ownership can be transferred to another user. All right. Then we have the second type of user, which is group. The group category includes users who have been grouped together for organizational purposes. That means a team. So groups allow you to efficiently manage permissions for multiple users at once. For example, suppose all developers might be in a dev group with special access to development tools and files. So what are the key characteristics of this kind of user? These kind of users can belong to multiple groups. They efficient for managing team access, and then permissions apply to all group members, can be nested for complex hierarchies. And then we have the third type of user, which is others. So the others category represents everyone else on the system who isn't the owner or who is in the group, who is not the owner or not in the group. This is essentially the public or anonymous access level. Permissions for others should be set carefully to maintain security while allowing necessary actions or uh, allowing essential access. So the key characteristics include applies to all users, not specifically categorized, should be restrictive for sensitive files. These kind of owners should be restrictive. All right. Can be open for public or shared resources and acts as a safety net for access control. So this three-tier permission system creates a flexible security model. We can give full access to the owner, moderate access to the group, and minimal or no access to everyone else. So this structure prevents unauthorized access while maintaining productivity for authorized users. Then how permissions look, the permission string. So decoding the pattern. See, when you run ls-l in Linux, you will see a permission string like -rw, xr, -xr, dash. So this cryptic looking string actually contains a wealth of information about who can do what with the file. So the string breaks down into four main sections, each revealing different aspects of the file's security settings. So let's dissect this step by step to understand exactly what each character means. So the first is file type character. The file type character indicates the file type. A dash means it's a regular file. A D means it's a directory. Other characters can indicate special file types like symbolic links, L, or device files C/B, etc. And then we have owner permissions. So the next three characters show permissions for the user or owner. For example, RWX written above on the screen, the owner has read, write, and execute access. All three permissions are granted. So that indicates. Next, we have group permissions. So the following three characters show group permissions. So in R-X, the group has read and execute access, but no write permission. All right. So the dash indicates that the permission is denied. And then we have other permissions. Other permissions means the final three characters show permissions for everyone else. In R dash, others have only read access. Both write and execute permissions are explicitly denied with dashes. All right. So using ls-l file name is your go-to command for checking permissions. The output also includes additional information like file size, modification date, owner name, and group name, etc. So this view helps us quickly assess whether permissions are set appropriately for security and functionality or not. So the execute permission is particularly important for directories. Without execute permission on a directory, we cannot enter it or access any files inside, even if you have read permission. All right. So this is a common source of confusion for Linux users that you need to be that needs to be clarified, and you need to be intuitive and not confused. All right. And then we have and this comes with practice, of course. And then changing permissions with chmod. Now you need to change the permissions. How are we going to do that? The chmod command is your primary tool for modifying file permissions. It stands for change mode and gives you chmod, which means change mode, and gives you the user, it gives you complete control over who can read, who can write, and execute your files. So the basic syntax is chmod, that means change mode, options, mode, file name. This command takes a mode specification and applies it to the specified file or files. So the mode can be expressed in symbolic notation using letters or numeric notation using numbers. Next is symbolic mode. So the syntax for symbolic mode for users: U, G group, O others, A all. Operators that are used, that can be used are plus, add, that minus, remove, equal to, set exactly. All right. So this notation is intuitive and easy to understand for beginners. Then we have numeric mode. So the numeric mode is a 3-digit octal numbers representation. More compact, it is more compact and preferred by experienced users. Also, it allows setting all user permissions at once. Next, common examples in action: adding execute permission. So this is the syntax. This adds execute permission for the owner. That means for the user of script.sh. So the owner can now run this file as a program while preserving existing read and write permissions. Okay. So next, removing write permission. So we have this syntax. It takes away write permissions from the group. Minus W takes away write permission. Group members can still read the file but cannot modify or delete it. Useful for protecting important documents. Then setting exact permissions. So here we have this syntax: chmod a is equal to rw file.conf. Sets read and write permissions for everyone, all users. All right. Removes execute permission if it existed. And the equal sign means set exactly this way. Next, common numeric pattern. So, the given example, what it does, it sets full permissions: RWX for owner, and read or execute RX for group and others. This is the standard for executable programs that everyone should be able to run. Now, what is 755? We will understand this in the next upcoming slides. So, the beauty of chmod is its flexibility, changing mode. You can modify permissions incrementally using symbolic notation or set everything precisely using numeric notation. So, for beginners, symbolic notation is more intuitive while numeric notation is faster and more commonly used in scripts and documentation. Okay. Next, we have numeric or octal permission codes. So, while symbolic notation is intuitive, numeric, that is octal notation, is the preferred method for experienced Linux users and in scripting. So, it's more compact and allows you to set all permissions with a single 3-digit number. 4. Read permission. The read permission has a value of 4. This represents the ability to view file contents or list directory contents. Then 2. Write permission. The write permission has a value of 2. This represents the ability to modify file contents or change directory contents. Then we have 1. Execute permission. This means the execute permission has a value of 1. This represents the ability to run a file as a program or enter a directory. So building permission numbers, how we are going to build the permission numbers? To calculate the numeric permission code, you can add up the values for each permission you want to grant. All right. For example, we have 7. All right. So 7 is equal to 4. That means read plus write 2 plus 1 execute, RWX. Then we have 6. 4 plus 2 plus 0 is 6. So read plus write is equal to RW minus. That means we have the read and write permissions are granted, but execute permission is not granted. Then we have 5. 4 plus 0 plus 1. Read plus execute. All right. Write permission is not granted. Remaining 2 are granted. Then 4. 4 is equal to 4 plus 0 plus 0. Read only. That means R minus minus. Only read permission is granted. So in this way, you can build permission numbers. The 3-digit code represent permissions for owner, group, and others in that order. Now we can go back to the previous slide, and here we can see chmod 755 program. So 755 program. 7 means all 3 permissions are granted. Then 5 means read and execute permissions are granted only. All right. So chmod 755 program. What it does, it sets full permission for owner. 7 for owner. That means all permissions. Read, write, execute. All 3 permissions are granted for owner. And then read, execute. 5. Read and execute. Only these 2 permissions are for group. And the 3rd digit for everyone or others. Others के लिए भी 5. That means read and execute permissions are granted, not the write permission is granted. All right. So in this way, we are going to build the permission numbers. Then we have 1. Owner, first digit is for owner. The first digit sets permissions for the file owner. Common value is 7, 6, or 4. Then we have 2. Group, second digit. Second digit is for group. Third digit is for others. All right. So the second digit sets permissions for the group. Common values might be 7, 5, or 4. And then the third digit sets permissions for everyone else. Common values could be 5, 4, or 0. All right. Then common numeric code 755, full access for user, which I have told earlier. So this is the example. Now understanding numeric notation is essential because it appears everywhere in Linux documentation. All right, next, moving on to next, we have changing ownership, ch own and ch group. Now ch own, changing file owner. The ch own command changes the user ownership of a file or directory. All right, here we have the syntax ch own user file name. And we have some examples shown on your screen. Similarly, we have ch group, changing group ownership. The ch group command changes the group ownership of a file or directory. We have a syntax ch group file name. Examples are shown on your screens like ch group developers code.c. So what it does, it changes group to developers. Then ch group are team docs. What it does, it recursively changes group for all files in docs directory. And then the third one, it changes group for all .txt files in the current directory. And similarly in chown, changing file owner. Example, chown alice report.txt. What it does, it changes owner to user alice. And then the second one, it changes owner to Bob and group to developers. Then third one, it recursively changes ownership of all files in directory. So only the root user or current owner can change file ownership. This prevents users from transferring ownership of sensitive files to others without proper authorization. Now, why ownership matters? Ownership determines which set of permissions applies to a user. When you try to access a file, Linux checks, or are you the owner? If yes, owner permissions applied. Are you the files group in the files group? If yes, group permissions applied. If neither applies, other permissions are used. All right. So understanding this order is important because it determines the actual access rights a user has. So one, owner check, is current user the file owner? Number two, group check, is user in the files group? And number three, others used, apply other permission. Then both chown and chgroup support the recursive -r recursive flag to apply changes to entire directory trees. This is particularly useful when reorganizing projects or when transferring ownership of complete directory structures. All right. Then we have special permission bits. What are these special permission bits? See, beyond the basic read, write, and execute permissions, Linux offers three special permission bits that provide additional functionality. And these are the advanced features used in specific scenarios to enhance security or enable special behaviors. Like set UID, represented using S. Set UID. So the set UID bit represented by S is in permission strings causes a program to run with the permissions of the file owner rather than the user executing it. So this is useful for programs that need elevated privileges to perform certain tasks. So examples might include, suppose we have password changing utilities that need access to /etc/shadow. All right. And then suppose we system administration tools that modify system settings. And then other example might include network programs that bind to privileged ports. Okay, so set UID. How are we going to set that? Chmod u plus s program or chmod 4755 program, 4 in the first position. All right, it sets the set UID. Set UID programs can be security risk if not written carefully. So only use on trusted programs. Then we have set GID. So the set GID bit has two functions depending on whether it's applied to a file or directory. For files, it is similar to set UID but runs with group privileges. Okay. And for directories, it causes new files to inherit the directories group rather than the creator's primary group. So when set GID is set on a directory, any new files or subdirectories created within it automatically belong to the directories group, not the user's default group. Setting set GID. How are we going to set the set GID? chmod g plus s directory or chmod 2755 directory, 2 in the first position. So shared project directories where multiple users need to collaborate with consistent group ownership include one of its common uses. Then we have sticky bit represented using T. The sticky bit represented by, it can be represented by small t or capital T in permission string, affects directory behavior. When set on a directory, users can only delete or rename files they own, even if they have write permission to the directory. So common examples, the /tmp directory typically has the sticky bit set. This prevents users from deleting other users' temporary files and while still allowing everyone to create their own temporary files. How we are going to set the sticky bit? chmod plus d directory or chmod 1755 directory, one in the first position. And lowercase t means execute permission is also set. Uppercase T means execute is not set. Okay. Now combining special bits, you can combine special permission bits with regular permissions. The numeric notation uses a 4-digit code where the first digit represents special bits. Like we have 4 triple X set UID. Okay, means 4 in the first position and then 755 or the permission you want to set. Then set GID 2 in the first position, then XXX, that means 2755. And then sticky bit 1XXX, that means 1755 or any other possibility. Then all three set 7, then XXX, all three set 4 plus 2 plus 1 is equal to 7. So 7 means we have the read permission, we have the write permission, and there is a execute permission also granted. So, like for example, we have chmod 4755 program. This sets set UID with RWX for owner and RX for groups or others. So these special bits are a powerful tools but should be used carefully. Misuse can create security vulnerabilities or any unexpected behavior. So always consider whether the enhanced functionality is necessary and whether it introduces security risks or not. Then we have summary and we have some practice also. So mastering the file permissions is essential for Linux security and system administration. Let's review the key concepts and explore practical tips for applying this knowledge. All right, so first is check current permissions. So how are we going to check the current permissions? We will use ls-l to view detailed permission information. And this should be your first step before making any changes. All right. Then we have set appropriate permissions. For setting appropriate permissions, use chmod to control who can read, who can write, and who can execute. So start restrictive and open up only as required or when needed. Then we have manage ownership. Use chown and chgroup to control which users and groups the permission apply to for managing. Then practice safely. Obviously, test on dummy files first. Then create a test directory and experiment with different permission combinations. All right. So now what are the best practices for security? We have principle of least privilege. That means only grant the minimum permissions necessary. Don't give write access if read only suffices. Don't give execute permission unless the file needs to be run. Then avoid 777 permissions. That means setting permissions to 777. 7 means all permissions read write execute for user. Then 7 read write execute permission for group. Then 7 means read write execute permission for others. Avoid all permissions for all users. This indicates use only for temporary situations or public directories where security is not a concern. If you want to use, then use only on limited situations, in limited situations. All right. Then regular audits. See, periodically review permissions on important files. Use find slash path type F permissions 777 to identify overly permissive files. Okay. and then use groups effectively. Create groups for different project teams or access levels. This makes permission management much easier than setting individual user permissions. Then common permission patterns. What are the common 755 programs and scripts, 644 regular documents. So the proper permissions keep your Linux system safe and efficient as well. So understanding these concepts give you control over your system security. Start with the basics: read, write, execute permissions for user, group, and others. Master chmod and ls-l first, then move on to ownership with chown and chgroup. And only after you are comfortable with these basics should you explore special permission bits like setuid, setgid, sticky bit. Okay, so okay, so that's all for this module, and thank you.